Hello, everybody. So what we're going to be looking at today is section 4.6 in your book, which is directional derivatives. Realize that that just says direction derivatives. So let's fix that. Directional derivatives. Hold on. There we go. Okay. And the gradient. So what are these? Well, we'll get into that in a second. What we're going to do is we are going to first of all figure out what is a directional derivative and how do we calculate it. Um, then after we do that, we're going to learn what a gradient is, which is going to be related. And then we're going to learn more about what the gradient means. And we're going to learn about some stuff involving level curves. Okay. And yeah, let's go ahead and get started. So let's look at a simple graph of a surface. I drew one already to save time. And there it is. So here's the idea. So you can pick a point on this graph. So we have a surface, z equals f of xy. And, that's going to be presumably something that's differentiable, but we'll get into that when we actually have to take derivatives. So we have a surface z equals f of xy. Now you can find a point AB in the domain of this function. So let a comma b be a point in the domain of f. So where is that on the graph? It could be anywhere, right? It's just anywhere in the domain. So if this is x, this is y, then AB could be anywhere where this function is going to be defined. So like, you could put it like right here, for example, which, I'm trying to draw that in the XY plane. It kind of looks like it's above zero, above z equals 0, because it looks like it's above the x-axis there. But maybe it's just to the left of the x-axis, like that. Okay, so it's still in the XY plane. Now, of course, if you have a point like that, then there's going to be a point on the surface or right above that point. Maybe it's right here. And yeah, there's going to be a point like that on the surface, and maybe it's right there. Pick a different color for that point. Okay, so maybe this point here is a comma b comma f of a b, right? Because the function value is giving you the z value. So you have a point there. Okay, now from that point, you can pick a direction. So like if we look in the xy plane, so like in the xy plane, you can choose a direction from the point AB. Now I'm just going to draw a little picture to illustrate that. I guess I'll draw it right here below it. Right, so you have an XY plane, and this XY plane here is just this XY plane. I'm just drawing it over here. And so the point AB is just wherever it is. I'm not going to try to draw it in any particular place. I'm just going to say, like, suppose that that's AB, for example. Okay, now when I say you can pick a direction, what I mean is you can pick a direction, right? From this point right here, you could go, there's a direction, or there's a direction, 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 right? Any direction from that point, right? So over here, that would correspond to, go that way, that way, that way, that way, back, that way, right? Like you can go any direction from there. And then if you do that from the point up there on the surface, you're going to get different kinds of slopes. That's actually what we're going to measure is a slope here. So like, for example, if you pick like a direction like this, I'll draw that one in blue, then maybe up here, that corresponds to this direction, right, on the surface. And maybe the function doesn't get smaller at all. But if you pick a different direction, like let's say I pick like forward like this, then that would be like pointing down, right? If it's on the slope there. And so depending on which direction you choose from this point here, AB, um, it could be uphill or downhill, or maybe the elevation doesn't even change at all, right? It all depends on what direction you pick. And anyway, the exact slope, right? Uphill, downhill, left, right, kind of slanted here. Um, that slope that you're going to calculate is what the directional derivative is going to be. So in the xy plane, you choose a direction from that point, um, right? And how does that work? So the way we do it is I'm going to come over here, continue on in blue, I guess, because that's what we were using. So you can choose a direction. Let's suppose the direction is can be a unit vector in the direction. So, it doesn't have to, like in principle, the direction could be a vector of any length, but it makes sense to use a vector with length 1. And the easiest way to do that in a particular direction is to say, we're going to go cosine theta I plus sine theta j. That's going to be our direction, right? So like, 0 is going to be straight out to the right. 90 degrees is going to be straight up. 180 is going to be out to the left, and so on, right? The normal theta that we normally use to get a direction there. Okay, so the direction can be listed that way. So you can get a new point here as like this, right? Hold on. So if you use this direction, which has unit length, right? Length 1, you can get a point, find a point in the direction of that unit vector. So I'm just going to say of u from the AB. That point could be what? So you can start at A, and then from the A, you're going to add some amount in this direction, cosine theta. And all of that's going to be I. And then from the B, the y component of this vector, you can add some amount in the direction sine theta, j. Okay. And if you put this point, actually, I want it to be a point, so I actually don't want the I and the j. Let me rewrite this right this way. So that point can be this. And so, for example, if I just erase some stuff on this graph here, that's too much. That's too much. Just erase what I want. Come on. That did it again. Okay, good enough. So if I put this point down here, there it is, right? And so that is a B. Now you head off in that direction, whatever direction it is. We don't really like care at this point, but just some amount in that direction. So like maybe I go like this, and I say this point right here, this could be A plus H cosine theta, B plus H sine theta. Okay, so that's just, again, in the xy plane. Okay, now where would that be up here? Well, where that would be here is just like maybe if you come up from that point, it's going to be somewhere else on the graph, right? So this point could be A plus cosine theta. Do I have enough room? I don't know. B plus H, sorry. B plus H sine theta. And then the Z value, man, do not leave enough room here. Okay. And then the Z value there could be F of A plus H cosine theta b plus h sine theta. Okay, so you get this other point here on the graph, right? So you've got these 2 points, uh, which we got here, and we got another one right here. And you can find the slope between those 2 points, okay? So if we find the slope between those 2 points, so what are the points? A, B, f of AB, and A plus H cos theta, comma, B plus H sine theta, comma, f of A plus H cos theta, B plus H sine theta. Okay, so what is that slope? That slope is this. So I'll call M and SEC. That's going to be the slope of the secant line. And the way you calculate a slope is it's like y2 minus y1 over x2 minus x1. Although in this case, what it's going to be is it's going to be the function value at the second point minus the function value at the first point. That's like the difference in y values. Although now it's the difference in z values because z is our height. So we got f of a plus h cos theta, b plus h sine theta, minus the other z value, which is f of ab over h. Okay, so if I put a little line segment on here, like right here, connecting those 2 points, this has slope m secant. Okay, and that's this one right here. So that's the slope. Okay, and now this looks like a lot like what you do when you're coming up with the definition of the derivative in a Calculus 1 class. And in fact, what we're going to do is we're going to say, well, if we let the h here shrink to 0, then this point is going to slide over to this point, right? Just like Calculus 1 definition of the derivative. So I'm not going to explain too much. I'm just going to write this definition. So definition. Suppose z equals f of x, y is a function of 2 variables. I'm not going to write that. It is, I wrote it that way. So suppose z equals f of x, y has domain D. Let a, b be in D, and define u is going to be our direction, cosine theta I, I said I, wrote j, plus sine theta j. Then the directional derivative of f in the direction of u is, so capital D for this derivative, u for the direction because the direction makes a difference, of f evaluated at AB is, and it's just going to be a limit as h goes to 0 of this slope. Okay, let's just rearrange this a little bit to make it fit a little better. Okay, do a little better than that even. Okay, good enough. All right, so that's our directional derivative. So capital D is going to be directional derivative. You see the subscript u that indicates the direction. This is the function, and this is the point where you're evaluating this at. Okay, so all of that is your directional derivative. And this is going to be provided the limit exists. Okay, now that is like a formal definition. I'm gonna like just kind of put a note here. Note, I don't think I've ever used this definition before in my life to calculate a directional derivative. Don't think I've ever used this definition to compute a directional derivative. Now, the book does. They suggest it like it's a good idea. Um, but I don't think it really is. I mean, it's you can do limits. I mean, there's nothing wrong with doing limits. So if you know how to do limits, you can do this limit and calculate a directional derivative. But there's going to be better methods for doing it. Uh, and yeah, I think we'll just use the better definitions for doing it. So I'll double check the homework before before deciding not to do it for real. But here's how we are generally going to calculate it instead. So instead, we're going to use a theorem. And actually, even this theorem is not how I do it. So it's going to be directional derivative. And this, I'm going to say how to actually calculate one, right? Because you don't use the definition of the derivative to calculate derivatives, 99% of the time. And the same is true here. So that's where I'm going with this. Okay, so let's see here. So this is what you actually do. So let z equals f of x, y be a function of x and y. I hate the way they do that. They write it as a function of x and y and then say let it be a function of x and y. It's like, well, it is. You can see it. So let z equals f of x, y, be a function. And fx and fy exist, right? So these are the partial derivatives of f with respect to x and y, right? Then the directional derivative of f in the direction of u is du f of x, y. So same formula as before. This time it says x, y instead of ab, but you plug in the x and the y that you want. And you simply have to do fx of xy times cosine theta plus fy xy times sine theta. Okay, so that's going to be a much easier, that's going to be a much easier formula to use, okay, rather than doing a big long limit. So I'm going to grab one of the questions that they kind of, actually, I'll just grab one straight from your homework. Let's do this. Okay. So this is straight from your homework. They say find the directional derivative of f of x, y equals 6x squared y to 3 minus 3x squared plus 2y minus 5 in the direction of theta equals pi. Okay, and they're not asking us to do this at a point. So our answer is going to have x's and y's in it. Okay, so how do we do this then? Right, so let me just kind of the idea here. So this is just for our understanding because we haven't done one of these yet, okay? So just so we're clear, you have an xy plane. Now, x comma y is some point on this plane, right? So like normally, like if you had a specific number, they'd call it AB, but we don't. So I'm just gonna say like there's a generic x, y. All right. Now from that direction, sorry, from that, did I call x, y a direction? From that point x comma y, we want to head out in the direction of theta equals pi. Now you know that we're using the normal like standard position type angles, right? So like that's 0 radians. This is pi over 2. This is pi, 3 pi over 2, and 2 pi and so on. That's the kind of directions that we're looking at here. So an angle of pi is going to be straight in this direction. Okay, so that's like pi. And that's your direction of u. Okay, now the interpretation of this directional derivative is going to be that the slope of the surface in that direction is given by this directional derivative. So let me say that the slope of f of xy, z equals f of xy, at the point xy in the direction of u is that directional derivative, d subscript u of f of xy. Okay, I'm just writing that just because we haven't done one of these before. I'm just making sure we understand what it is we're calculating here, right? Like, again, from the picture, right? One direction, the function might stay constant. Another direction like this one, maybe the function goes down. Another direction, maybe it goes up, right? All just depends. So that's what we're doing here, and that's what we're trying to calculate. So in order to actually calculate this though, right, so that we have our solution, we're referring to this theorem here. What we're going to need is the partial with respect to x and the partial with respect to y, and we need to know that theta if we're going to use this formula. It's not the only formula, but we need it for this formula. Okay, so let us do this. So find the partials first. Okay, so we need fx and we need fy. And I'll just copy this. Again, I will copy this, duplicate it, come down here just so I can look at it while I'm doing this. And let's go. All right, so we're doing a partial with respect to x first. So we're treating the y as like constants. So the derivative of 6x squared, of course, is going to be 12x. And the y cubed is just carried along. So 12x y cubed. The derivative of negative 3x squared is going to be negative 6x. And nothing else has an x, so that's the end of that derivative. Then we need the partial with respect to y. So partial here, we're going to take the derivative of the y cubed. It's going to be 3y squared. Combine the 3 with the 6, and we get 18 x squared y squared. Then plus, there's no y's here, so that derivative is 0. The derivative of 2y is going to be 2. And there are no more y's, and so that's it for our directional derivatives. So we have these two directional derivatives here. We don't need this anymore. We have our angle. They told us it as theta, right? They gave us theta equals pi, right? So our formula then, which is right here, just needs us to substitute our stuff in. So since this is our formula, we just plug in our stuff. So the directional derivative in the direction of u of f of xy is fx, which is this. So parentheses, 12x y cubed minus 6x, cosine theta, which I'll write it just right now, cosine pi, plus fy. Fy is 18x squared y squared plus 2. and then times sine theta, which is pi. Um, Notice that this is a number because it is a slope in a particular direction, right? So this is a number, which makes sense because it's a slope. Number, not a vector, is what I'm saying. This makes sense because we said it's a slope. Okay, just again, trying to make sure we have some idea of what we're doing here. Now, what happens now? Well, we just need to calculate these two things, just cosine pi and sine pi. Since we know that cosine pi is -1, and we know that sine pi is 0, at least I hope we know that, then what we're going to get here is this is going to be just simply, this is a -1, so we're going to have negative 12x y cubed minus 6x, and then that's it, because this one is 0, right? So let me get a color here, right? So this is -1, and then this is 0, which means this is all we have left down here for our directional derivative of f in the direction of u. Okay. Now, if you pick a different direction, then you're going to end up with a different directional derivative, of course. Okay, let us do maybe at least one more. Okay, yeah, that's a good one. Okay, let me, I like this problem that I found here. Let me just double check if they give us this they give us an example here. Blah, blah, blah. They got a gradient, they got a gradient again, they got a property of the gradient. Dum-dum, maximum derivative. Okay, yeah, they don't do it. Very strange. It's a little bit weird of your book. Um, but I'm sure it's in the homework, so let us continue on here. Okay. So, um, actually, yeah. Okay, you know what? I want to, okay, sorry. I was looking at your book. I was surprised at what they did, but let us move on and let's talk about a gradient now, and we will do more directional derivatives momentarily. Let's go. Okay, so what's next? Gradients. Okay, good, 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 good. We will come back to directional derivatives in a couple minutes. Gradients. Okay, so this is going to be just a definition here. So this is going to be just, this is what a gradient is. Definition. Let z equals f of xy be a function for which fx and fy exist. So that's just the same as the previous theorem. The gradient of f denoted, got a weird symbol, new symbol for you guys, upside down triangle here, f of xy. This gets called grad f, by the way. So denoted that way is defined as grad f. I'm going to write that in a second, that's how people say it, but grad f, and it's just this vector. So it's a vector, first of all. It is f subscript x, so partial of f with respect to x, I plus fy xy j. Or, if you write it in the triangular brackets notation, then you're just looking at fx, comma, fy. Okay. Um, Often this symbol like this is read out loud as read or written grad F. Okay. So this is like the old school way to do it because you don't have to go too far back before people were trying to type math on typewriters, right? Not so far long ago. And of course, you don't have all these fancy like Greek letters and things on a keyboard. It was a pain. So if you didn't have to use those symbols, they didn't necessarily use them. Um, so they wrote grad F when they meant the gradient of F. Uh, so that's the gradient. Um, it's just sticking the partial derivatives into a vector. Okay, and the reason we care about it is because it gives us another way. Well, among other things, it gives us another way to calculate a directional derivative here. Okay, so so another way to compute the directional derivative is, so by definition, um, that's not the symbol I wanted. I wanted the directional derivative in the direction of u of f of xy is grad f xy dot product with u. And that's where u is a unit vector in the direction that you want. Okay, where u is a unit vector in the direction you want. Right? So u is supposed to be specifying a direction. Now, why would you use this formula here? You would use this formula just because it's more convenient when theta is not given to you, right? Like the formula that we have up here is pretty convenient when you're given the theta because you just put in the theta, cosine theta, sine theta. But actually, like even this, if you write like u equals cos theta, comma sine theta, that is a unit vector. Cosine theta, sine theta is a unit vector. And if you just take this right here and you put it right here, then that's how you get that formula, right? So I'm going to just demonstrate this real quick. So uh, if u is cos theta, sine theta, like we had before, then directional derivative in direction of u of f of x, y is it's grad f. I'm leaving off the xy right now. Dot u, and grad f we know is the vector f subscript x, f subscript y, dot cosine theta, sine theta, and if you do that dot product right, then you get f subscript x. I'll put the xy in now. Cos theta plus fy x comma y sine theta, which is of course the same formula that we already had, right? Okay, so this is all completely consistent, but just by kind of habit, this is the formula that like I would go for if I wasn't told theta. Okay, So I use this when they don't tell me theta. Okay. Now it doesn't matter. I mean, they're the same formula, but this is the one that I tend to use. Okay, so let us do a problem real quick. So let me go here, pick one off the list, and I'm going to say to do two things here. So I've got a function. So let f of xy equal negative 2x cubed y plus 4x squared y squared minus 3xy. And I want two things. The first thing I want is I'm going to say find grad f, the gradient of f. Find grad f. Second thing, I'm going to say find the directional derivative in the direction u of f of xy where u is in the direction of v equals 1 comma 2. Now, just one thing I want to get out of the way before we start this. Look what I did here. I said this is the directional derivative in the direction of u. And I said where u is in the direction of v, right? So this is a v, not a u. Why is it a v, not a u? Because I was being a little bit sneaky here. The u is a unit vector, right? Unit vector means length 1. So this is not a unit vector, which means you can't use it directly. Like you can't use this v in this formula right here. It has to be a unit vector in order to use the formula. Okay, so that's just first off. I want to remind you, like, be on the lookout for that because that's a common mistake to make, thinking you can use that v in place of the u, right? V is not a unit vector and can't be used directly in the formula. For D. Okay, so, all right, let's go ahead and get started now with this problem. All right, so number one, we want to find the gradient of f. Now, remember, the gradient of f is just the partial derivatives in a vector, right? Gradient of f is simply partial with respect to x, comma, partial with respect to y. Super simple, okay? So conceptually, the gradient of f is easy to calculate. We just need two derivatives, partial derivatives. And we don't really need to list them separately. Let's just put them in the vector to start with. Okay, gradient of f. So we need our partial with respect to x, and I can see the function right here, so I don't need to copy paste it. Let's go. All right, we're taking a derivative with respect to x. So here, there's only one x, it's right there. Derivative of x cubed, of course, is 3x squared. So we're going to end up with negative 6 x squared y plus, now we need the derivative here. So the derivative of x squared, of course, is 2x. So we're going to end up with 8x y squared. We got another x. The derivative of negative 3xy is going to be negative 3y, right? Because the derivative of x is 1, so it's going to disappear off there. Let's write that correctly. Okay, so there's your partial with respect to x. Now you do the partial with respect to y. So we're going to get negative 2x cubed plus, looks like the derivative of y squared is 2y. So 8x squared y. And then finally, for the last one, it's going to be negative 3x. All right, so there's your gradient. Okay, so it's just the partial derivatives stuck in the vector there. Okay, very simple. All right, now once you have that, now we can do our directional derivative. Directional derivative of u of f of x, y, given the v was 1 comma 2. Okay, so we can't use the formula yet. You actually have to find the unit vector. So first thing is going to be um, find a unit vector first. Now it's easy. You know how to find unit vectors. It's something you've done a number of times in the past, right? You're just going to take the vector v and you divide it by its length, and that makes it a unit vector. So this is simply going to be 1 comma 2 over the magnitude of 1 comma 2, which is 1 comma 2 over square root 1 squared plus 2 squared. So it is 1 over square root 5 comma 1, nope, 2 over square root 5, right? Let me rewrite that. Kind of cheated here, right? So that's square root 5 in the denominator there. You can rationalize the denominator there if you want to. I guess I will. Why not? If you rationalize the denominator, you're going to get square root 5 over 5 and 2 square root 5 over 5. Okay, so there you go. You found a unit vector in the direction. So this is our u. Then now we can use our formula. For the directional derivative. So the directional derivative in the direction of u of f of x, y is grad f dot u. So we need the grad f. It is somewhere. Oh, kind of long and complicated looking. Let's actually give ourselves some more space. Come on. That over there. Okay. Dot the u, which is radical 5 over 5, 2 radical 5 over 5. So how are you going to do this? Well, I mean, there's not a lot to it. You're doing the dot product. So you multiply first component, second component, and you add them. So really, like, there's nothing difficult here. You're just like kind of just writing out a lot of stuff. There's the first component of the first vector. You multiply it by the first component of the second vector. And then plus the second component times the second component. And you're done. You are done. There's your directional derivative. Okay, so you'd actually have to plug in a point if you wanted a slope at a particular place. Okay, let us. Okay, that's find the gradient. That's too easy. All right. Let's do one of these. We haven't done one of these where it's in a particular at a point in a particular direction. So actually, okay, you know what I want to do? I'm making one up. I'm not using the one in the book. Let's see. Find the directional derivative of f of x, y. This could be anything. I'm going to go e to the, I'm going to go x squared e to the xy. At p negative 2 comma 4. And they say in the direction of the point Q, which is 3 comma 4. Okay, so we have everything we need to do this problem, but because we haven't done one of these before, it's going to, feel like there's a little bit of extra work there. Okay, so we can do the gradient already, but we don't know our vector. Um, we don't know our vector u or even v yet. Okay, so that's kind of the thing that we have to look at. So they didn't tell us the vector specifically, right? So they told us f and the point, but they didn't give us the vector u or even a vector v in the direction we want. Okay, you have to calculate it from what they said. But they said the direction was from P to Q. Right? So look at the way they worded this. I copied the wording from the book. So they say, or sorry, from your homework. They say find the directional derivative of this function at this point, but then they say at this point in the direction of the point, this other point. So at this point in the direction of this point. And so your vector, like on an xy plane, which I will draw, you got the point negative 2 comma 4, right? Negative 2, 4, and that's P. You've got Q, which is 3, 4. Like that. And so your direction is here. And that's the direction V, not U, because that's probably not going to be a unit vector. Okay, so that's what's going on, is they didn't give you that vector. Okay, so maybe before we start, let's just calculate that vector. So the vector V is the vector from P to Q. And the way you calculate a vector from one point to another point is you subtract, right? So the x component is going to be 3 minus minus 2, and the y component is going to be 4 minus 4. So your vector v is going to be 5 comma 0. That's your v. Does that make sense? Oh, did I copy these down wrong? Hold on. Oh, I did copy them down wrong, but we're going to use the ones that I wrote. In the actual example, there was a negative there on that 4. I was wondering why it worked out 0 there for one of the components, but it doesn't matter. It did because it did. All right, so you have that vector v. Now, technically, you need a unit vector in the direction of v. You could guess it, right? Like on this one, if you need a vector with length 1 in this direction, of course, it's just 1 comma 0, right? 1 comma 0. But, we could calculate it the same way as we did in the previous example in general. So I'm just going to write that because maybe somebody will look at this example and need to follow it. So, so the unit vector, right, which is, obviously 1, 0, but can be calculated as the unit vector is v over the magnitude of v, which is going to be 5 comma 0 over the square root of 5 squared plus 0 squared, which is 5, 0 over 5, which is 1, 0. Okay, so of course you didn't need to do that work, but you could, right? So you have that. We needed to work out that unit vector before we could do this. We did. So now we have the right direction, 1 comma 0. That'll be nice. The other thing we need is, of course, we need the gradient of this function here. Um, so let's do that. Uh, we also need gradient f. Just copying this and moving it down. So we need that gradient f. That's not going to be too hard. We're just doing partial derivatives. I did make it slightly trickier than normal because, right, you have an x here and an x here, and that means product rule. We have to do the product rule. So for this derivative, for the x derivative, we're gonna have to do the product rule. So it'll be like um, fg for the product rule. So f prime is gonna be 2x g. So that's f prime g plus fg prime, which is x squared. Then you need the derivative of e to the xy. The derivative of e to the xy is going to be e to the xy times the derivative of what's inside. So what's the derivative of xy with respect to x? Derivative of xy with respect to x is simply y. So there's your x derivative. Now you need your partial with respect to y, which will be much quicker. The derivative with respect to y, there's only one y here. So the derivative of e to the xy with respect to y, right? Partial with respect to y, partial of e to the xy is simply going to be e to the xy times the derivative of what's inside. But the derivative of xy with respect to y is going to be x. So you're going to have that x combined with those, and it's going to be x cubed e to the xy. And there's your derivative with respect to y. Okay, so we did that. So we've got our gradient. Okay, so now we can figure out the gradient, not the gradient. Now we can find out the directional derivative in the direction u. So now directional derivative in the direction u at xy is, we know, grad f dot u, which is going to be this because we just calculated it, dot product with your direction, which was just 1, 0 in this case. So it's 2x e to the xy plus x e, what? Plus x squared y e to the xy. I rearranged that a little bit. Okay, so there is your directional derivative. Now, this is what we've done in the past example, but I didn't want that. I actually gave you a point. I said I wanted this evaluated at, I said find it in the at -2, 4. We actually have to plug that in. Get a number, right? So since the problem said at p, which was -2, 4, not positive, not -4 because I wrote it wrong. Okay, yeah, -2, 4. We still have to evaluate that. So we have to go d in the direction u at -2, 4. We have to put those numbers in here. So you have 2x, which is -2, e to the x times y, -2, 4, plus x squared, which is -2 squared, times y, which is 4, and then e to the -2, 4. So we get -4 e to the -8. And then for the other one, we get, looks like 4 times 4, which is 16, e to the -8. So overall, we end up with 12 e to the -8. And that would be our directional derivative. Again, it's a number because it's a slope in a particular direction. Okay, so that's kind of the whole story as far as calculating directional derivatives. You can do it at a point, you can do it, you can just leave the x, y in there, just like regular derivatives. But we're not done yet because we need to learn some more interpretations of what the gradient does. Okay, so the gradient has certain properties. They are here. Properties of the gradient. So, let z equal f of xy, let's say, be differentiable at a point. Right? So you can calculate the derivatives at the point, which means you can calculate the directional derivative at the point because the partial derivatives give you the directional derivative. So we got a function where this applies. Now, here's our first property. So if the directional derivative evaluated at x0, y0, uh, I said directional derivative. If the gradient is the zero vector, well, think about what that means. You know your formula, right? Like, let me get this formula for the directional derivative here. Where is? There it is. I want the box. Duplicate. So we want to look at this while I'm writing these rules down here. So think about this. If this is the zero vector, right? So this is the zero vector right here. When you dot product the zero vector with another vector, you're just going to get zero, right? So if the gradient is zero, then the directional derivative is also going to be zero for any or every direction u. Right? It's obvious from the formula because, of course, if you dot product zero with something, you get zero. Okay. What else do we have? Another property we're going to have is that if the gradient is not zero, so we're not looking at zero derivatives, so it's not the zero vector. One of them can be zero, right? But there's two components. Then how should I say this? I don't like the way they said it, but I guess that's what I have to do. All right. So then the directional derivative of f evaluated at x0, y0 is maximized when u points in the same direction as the gradient. Okay. Okay. And they go further, and the maximum value of that gradient or of the directional derivative also can be calculated. And the max value of the directional derivative in the direction of u of f evaluated at x0, y0 is the magnitude of the gradient, whatever that is, evaluated at x0, y0. Now, that's hard to understand. Like, it's just kind of because there's so many words there. But basically, what they're saying is this. They're simply saying that the gradient which is a vector, right, points in the direction where the function is climbing the fastest. Right? It points in the direction that's most uphill. Okay, so like if I just draw a little picture here, um, like if you took if you took like a place like right here, and let me just say like, let's just say that that's centered at 0, 0. Um, like if you come down here like this, and you find that point, and like let's say that point is like AB, like what point does the direction, what point does the gradient point in? Well, where's the peak, right? Like this is downhill. You know, this is like if you're following that curve, the function is not getting higher or lower, right? But if you head towards this origin, towards the z-axis, right, then towards here, the function is going way uphill, right? So that direction, that's the direction the grad f would be at AB. Because that's the where the function is, you know, climbing the fastest is in that direction. Okay, and so that's all we're saying there. So it looks complicated, but like what's the direction where the function's going up the most? And it just happens to be the gradient. We haven't justified that, but it is. Okay, what else can we do? Well, another thing we can do is we can just note that what this also means is that the opposite direction is the most downhill. Um, so that's actually the, I guess, the third thing. It's just that. So if, again, the gradient is not the zero vector, then directional derivative of u of in the direction u of x0, y0 is minimized, which actually it doesn't mean like zero, right? Minimized means like most negative, right? Right, not zero. Um, in the opposite direction of the gradient, right? So this one, negative gradient. Okay, and also we can do the minimum value as well, just like the other one we said what the maximum value was, and the minimum value of du fxy is negative magnitude gradient. Right, so it's just the same as the other property, but with minuses. Okay, and the reason that that makes sense should be pretty obvious from thinking about the picture here. Um, if uphill has a slope of 3, then doesn't downhill have a slope of -3, right? So it's a pretty simple idea. If uphill has a slope of, let's say, 3, example, then the opposite direction, like if you turn around, Okay. Um, yeah, so like if this was slope 3, the red arrow that I put, which is now a blue arrow, then the opposite direction, it's the same slope. It's just, you're turned around and you're looking at it from the other direction. So those are those properties. So you need them because problems are going to specifically ask you to use them. Um, and if you don't know about the theorem, then you can't do it. So let's do an example. Uh, find the direction uh, for which the directional derivative of g, hey, they gave it a different name this time, equals 4x minus xy plus 2y squared uh, at, we need a point, negative 2 comma 3 is a maximum. And then also they say, what is the maximum value of the. So those are two different questions there. All right. So let us try to solve this. All right. So again, you need to know that theorem, right? So, um, the theorem said the max directional derivative was in the direction of gradient, in this case, g. So, I mean, that's easy, right? So we just need gradient g. So what's the gradient g? Well, we're just taking partial derivatives again, right? So we're taking partial with respect to x. So partial with respect to x. So derivative of 4x is 4. Derivative of xy is going to be negative y. That's it. Comma. Um, partial with respect to y. So partial with respect to y of 4x is 0. Of negative xy is negative x. And of 2y squared is 4y. That. Okay. Um, they asked for this at a point, negative 2, 3, so we have to plug that in. Right, the given point. Gradient g, evaluated at negative 2 comma 3, is 4 minus the y value, negative x plus 4y. So what do we get? 4 minus 3 is 1. And then we got negative 2 is 2 plus 12. So 14. 1 comma 14. Okay, so that's the direction. So direction where the directional derivative is maximum. Now, okay, so here's the thing. You get this gradient here. They probably want a unit vector in that direction. Um, so let me just check this real quick in the book. Or in the thing, but probably they want a unit vector in that direction. They don't want you just to say in the direction of 1 comma 14. They want the unit vector in that direction, I would imagine. So I'm just checking how they want the homework done here. Maybe they don't care. I don't think they care actually, but just in case they do. Okay, you know what? We'll just do it. So, um, okay, direction where G increases most or fastest. I'm just say where du xy is maximum is 114. But they probably want a unit vector. Then u could be, again, 1 comma 14 over the magnitude of 1 comma 14, which is, well, you got to do 1 comma 14 over square root 1 squared plus 14 squared, which I don't know what that is. I feel like I should have a calculator sitting here somewhere. Where is it? Okay, well, I don't. So I will just use a computer. Wolfram. 1 plus 14 squared. 197. And then square root 197. Probably nothing. It is nothing. Okay, so that's square root 197. So you could just write it as, 1 over square root 197, comma, 14 over square root 197. Okay, so that is the direction. Okay, and then for the second part, it says find the direction for which the directional derivative of this is at a maximum. And then they say, what is the max directional derivative? And so what is the maximum? It is by definition, right? They said it's the magnitude of the gradient evaluated at the point, which was whatever it was. The magnitude, and we just did it, right? That was magnitude of 114. That was the gradient. So it is square root 197. It was right there in the denominator. Okay, so yeah, so that's that. Uh, I guess I can double check this. No, I can't actually. Okay, okay. So that's it. So last topic, gradients and level curves. Okay, so let's just consider some level curve. I'm going to draw a picture, okay? So for some function, so we're just looking at the level curve for some function z equals f of x, y. Okay, and presumably the directional derivatives exist and all that. I'm not writing them right now. We're just looking at some level curves. Okay, now these level curves could be any kind of level curves here. Don't want to get too fancy here. Let's put a point there. Let's call that, I'm going to label it with the z values. Okay, so like let's say that is z equals like 10, for example. Okay, and then let's say I've got this, and that's like z equals 8, for example. And then let's see, I have one like this, and that's like z equals 6, for example. Then I got another set of level curves. Let's say that's z equals 4, z equals 2. And that's probably good enough. Okay. Um, so there's some level curve, right? And so you can tell from the level curves here that I labeled, z equals 2, z equals 4, z equals 6, z equals 8, z equals 10, that what's happening is, um, like from here, this is relatively low, and then it's up by 2, up by 2, up by 2, up by 2, right? So this way is the direct, like from here to here, climbing, right? From here to here, the function's climbing. From here to here, the function's climbing, right? Like this is like a topographical map. Z equals 10 is at the top, and then everything else is lower. So like this is like the peak of the map, right? Looking at that level curve. Okay. Now, one thing you can think about here is this idea. So, right, so the function does not change along a level curve, right? Like let's say you're right here. If you travel this direction or this direction, the function is still z equals 4, right? So if you are at a point, level curve, and move parallel to the level curve, I'll just say move along the level curve, the function doesn't increase or decrease, right? Like this is z equals 4. So if you just go around in circles here, the function is z equals 4 the entire time. So if you're on a level curve and move along the level curve, the z value doesn't change. That's what makes it a level curve, right? That's why they're called level. The z value doesn't change. Okay, what does that mean in terms of the directional derivative? The derivative is the slope, right? So if the function is not changing, then the slope is 0. So this means that the directional derivative at a point is 0 in the direction of the level curve. In the direction of a level curve is 0, right? Just like I drew. Okay, now here's another question. What is the direction of maximum increase? What is the direction where the function increases the fastest? We actually know the answer to that because it was what we just talked about up here, right? Like the direction in which the function increases the fastest is the direction of the gradient, right? Like if the gradient's not 0, the directional derivative is maximized, so steepest slope, when u points in the same direction as the gradient. So most uphill is the direction of the gradient. Now, on the picture, what is the direction of most uphill? Well, it's actually going to be 90 degrees away from the level curve, turns out. Okay, so the direction 90 degrees away from the level curve is the direction the function increases or decreases the fastest. We know that from the previous part that that's actually the gradient or the opposite of the gradient direction. So like on the curve here, I'll pick a different color. That would tell you that this is the direction that the gradient points, and this, the opposite direction, is the negative gradient. Now, how do I know that this is the one that's gradient and this is the one that's negative gradient? Well, remember, gradient points in the direction where the function's increasing. So if this is z equals 4, 6, 8, 10, this is the direction where it's increasing, and this is the direction where it's decreasing. Okay, and furthermore, these are 90-degree angles here. Okay, and so there's your picture. So we know now that the level curves are 90 degrees away from the gradient. Okay, so that's what we know. So there's a picture illustrating that concept. You got the level curves here, the gradient's 90 degrees away, but there's 90 degrees that way and 90 degrees that way from the level curve. So one is uphill and one is downhill, and 90 degrees away is the level curve where the function doesn't change. So that's what we know. Okay, so let me write the actual theorem. So suppose z equals f of x, y has continuous partial derivatives. And they say in an open disk centered at a point. They could have just said everywhere. That would have been fine too, but you know, they kind of want to make this, I don't know, they only want to require what it needs to require. Okay, so you got a function that has continuous partial derivatives. So what they're going to say then is if the gradient f of x0, y0 is not 0, that looks just like the other conditions that we already learned about the directional derivative, right? But I don't know why this one was not listed with the others. Then gradient f is normal. Now remember, normal means just perpendicular or 90 degrees away. Or orthogonal means the same thing. To the level curve of f at x0, y0. Okay. Now, there is what we have to do a sample of this before we stop. It's been an hour and 24 minutes, but we need a sample because, like, how do you find a vector that's orthogonal to another vector? You do not need a cross product for this. So that's why I want to do this. So let's see here. Okay. Example. I guess we'll just do their example. You know what? No, I don't want to do theirs. The ones in the book are so simple, and the ones in the homework are harder. Let's do this. This is straight off the homework. 4 f of xy equals square root x squared y plus 4x squared. They say find a unit tangent vector to the level curve at the point 1, -1, -1, 1. Okay, we can do this. We are okay. So we know that it's related to the gradient, specifically as 90 degrees away from the gradient. Okay, so from the theorem that we just talked about, we know the level curve is orthogonal, or 90 degrees away, to the gradient. So we have to find the gradient, because that's what we know how to find, right? So find the gradient. So we're going to need the partial derivatives here. So let me just make this a little smaller. Yeah, so we need partial derivatives. So we need the gradient of f. It's going to be, how do we do it? So we're taking the derivative of this function with respect to x. So I know I've said this before, I'll say it again. You want to remember that the derivative, you want to remember that the derivative with respect to x of square root x is 1 over 2 square root x. Makes your life easier. So when we're doing this derivative, which is a square root, it's going to be 1 over 2 square root x squared y plus 4x squared, and then times the derivative of what's inside with respect to x. So the derivative with respect to x of what's inside is going to be 2xy plus 8x. Okay. Do the same thing for y. So the partial with respect to y is going to be 1 over 2 square root x squared y plus 4x squared times the derivative of what's inside with respect to y. So the derivative of x squared y with respect to y is x squared, and that's the only term that has any y's. So there's your gradient. Okay. Now we don't need the gradient there, we need the gradient at the particular point, right? -1, 1. So we need it at, we need to evaluate it. Grad f at -1, 1. So we put that in. So let's do that. So grad f -1, 1 is going to be, just got to put our stuff in. So this can be in the numerator here. So in the numerator, you've got, I guess we don't need parentheses. In the numerator, we're going to have 2x y plus 8x. Okay. And in the denominator, we've got 2 square root x squared y, so -1 squared 1, plus 4x squared. Okay. For the other one, numerator is x squared. Denominator should be exactly the same. I'm lazy. Duplicate. Okay. So there is that. Now we got to evaluate the numbers here. So in the numerator, you've got 2 times -1 is -2, plus -8. -2 plus -8 is -10. And then 2 square root, what do we got in here? 1, this is all 1, plus 4. So square root 5, it's just square root 5. Okay, and the other one's going to be 1 over 2 square root 5. All right, so what do we get? We get, what do we have? -5 over square root 5, comma, 1 over 2 square root 5. If you want to rationalize the denominators, you can. You get -5 square root 5 over 5, and square root 5 over 2 times 5. So we get negative square root 5, comma, square root 5 over 10, I guess. Okay, you don't really need to do that. You could have just left it in the previous form. But in any case, that's your gradient. Okay, that's not the answer to the question, though. That's the gradient. So on the level curves, here's what's going on. Okay. So what you've got going on is negative 1 comma 1 is a point, right, on the xy plane. So you got this point, negative 1 comma 1. All right. Now then you've got this direction. That's the gradient vector. Now, like square root 5, negative square root 5 is pretty far in the x direction, in that direction. And then divide that by 10, and that's how much it's going up. So the gradient is basically like an angle like this. Um, so I mean, I'm not going to try to graph it perfectly, but like gradient f is something like that. Okay. Now, the what we want is 90 degrees away from that, though. Okay, so we need somehow to find something that's 90 degrees away from that. Okay. Also, they want a unit vector, which means we're going to have to find a unit vector in that direction. Okay, so let's continue on. So that's the gradient. Let us do two things. We need, did I number this? One, okay. A unit vector, first of all, that is 90 degrees away from, this gradient f that we just calculated. So I drew gradient f here, right? So what we need is oops, I want a different color. We need this vector or this vector, right? That's what our level curve is doing. I know that's what our level curve is doing right there because it's supposed to be 90 degrees away from that gradient. Okay, so we calculated this, but our answer is one of these. Doesn't matter which one. So does that make sense, right? You calculate the gradient that's away from the level curve. They want in the direction of the level curve. That's what they mean when they say tangent to the level curve. Okay, so we need a unit vector that is 90 degrees away from grad f, so that it is tangent to the level curve. Okay, so this is just kind of a trick here. Um, so trick. You know that orthogonal implies that like u dot v. I don't want to use those. I'll use different ones. Um, like if you do the dot product between two things and they're zero, then that means they're orthogonal, right? So you remember that 90 degrees away means the dot product is going to be zero. And the reason you want to remember that is because if you ever have a vector like this, so if you have any vector, I already used A and B. So what are letters? C and D. So any C comma D vector is orthogonal to if you just switch the two components around like that, and then you make one of them negative, that's orthogonal, right? And that's easy to see, right? Because if you just do this, C comma D dot negative D comma C. If you do that dot product, right, it's C times negative D, which is negative CD plus D times C, and that's zero. So if ever you're looking for an orthogonal vector and you've got a two component vector, oops, if you have a two-component vector, all you've got to do is just switch the components and add a negative sign to one of them, and you find an orthogonal vector. If you're in 3 dimensions and you want an orthogonal vector, then you're looking at cross products and things. But this is easier than that. So that's what we have. So right now we have this. So um, we have grad g evaluated at -1, is some vector, right? We got that somewhere. Oh, it's called f, not g, sorry. So we have grad f, and it is -√5, comma √5/10. So what is a vector that's 90 degrees away? We can do that, right? Just switch the components and add a negative. An orthogonal vector is, I'll just call it v. We're just going to switch the components. So √5/10 first, and then -√5 for the second component. And then you have to make one of them opposite sign in order for it to be orthogonal. It makes sense just to take this one and make it positive, because then there's no negatives involved. And obviously, if you do the dot product between these two vectors, right, these two are going to give you what, -5/10, and these two, when you do multiply them, are going to give you +5/10. So obviously that will work. Okay, so that's how you get a direction in the direction of the level curve. And then if you want it to be a unit vector, you still have to normalize it. Okay. But we were asked for a unit vector. So we have to do that. U is going to be v over magnitude v. So √5/10, comma √5 over square root √5/10 squared plus √5 squared. So tedious. So we square this. What do we get? We get 5/100. Is that right? Yes, it is. Plus 25. No. √5 squared is just 5. 5. Okay. So what is that? 5.05, I guess? Yeah, okay. Um, oh, I see what they do. So, yeah. I mean, you can work this out however you want. I see what the book does is this. They go like this, 5/100 plus 500/100. That's how they write the 5, right? 5 is 500/100, because then they can go √5/10, √5, and then in the denominator, you've got square root 505/100. But you can split that into √505 on top, and then on the bottom, the square root of 100, which is 10. And then dividing by 10 is the same thing as putting the 10 up in the numerator. So you have 10 square root √5/10, 5 over √505. Multiply that 10 through, you get square root 5, 10 square root 5 over square root 505. And you can rationalize that, but you know what? I'm not. I'm done. I've decided I am done. Type that into Wolfram Alpha if you want it normalized. Just leaving it. Okay, so there's your unit vector. And the point is that like V or U point in those directions. Actually, let's see which one's which actually. So we took this to be the one that's positive and positive. So yeah, that was V. And U pointed that same direction. V and U actually point in that direction. Okay. And technically, this would be the opposite direction. But if the level curve goes in one direction, it also goes in the other direction from that point. Okay, so that was how to do that. So I think that's all the problem types that are on the homework. I guess I could be wrong. I'm just gonna click a couple of times before I end this video just to make sure. Unit normal vector to the level curve. Okay, you know how to do that. That means just don't switch the components. Okay, almost. Okay, yeah, that's it. Excellent. So that's it for this lecture. It's not as bad as it seems. It only got kind of long because of all the extra theorems that we had to add. It still boils down to finding the gradient and then doing a thing, right? But what thing depends on what you're being asked to do. Okay, so that's it for now, and I will talk to you guys later.